Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science. And in this video, we're going to do an example with directional derivatives. So here we want to find the directional derivative of the given function at the indicated point in the direction of the given vector. So here we have the function f of xyz is xy squared minus 4x squared y plus z squared, and the point is 1, negative 1, 2, and our given vector is 6, 2, 3. So remember, in general, the directional derivative formula says we have to take the gradient of our given function and dot it with the unit vector in the indicated direction. Okay, so we don't have a unit vector. We have this vector here, which we can see from the 6, 2, and 3 is definitely not a unit vector. So we have to find the unit vector, and we also have to evaluate the gradient at this point. So let's go ahead and find the unit vector first. So let's go ahead and call this vector v, and we're going to want to find the unit vector, which is going to be unit vector equals v divided by the magnitude of itself. So we have to go ahead and find the magnitude of v. Now the magnitude of v is, let's fix all this. The magnitude of v is the square root of this squared plus this squared plus this squared. So that's going to be 36 plus 4 plus 9. And 36 plus 4 is 40. 40 plus 9 is 49. So we have the square root of 49, which is just 7. Okay, so that's good. So the magnitude is 7. So then our unit vector is 6 over 7, comma 2 over 7, comma 3 over 7. Because this here means we can divide each term in v, or each component of v, by the magnitude. So 6 over 7, comma 2 over 7, comma 3 over 7. Okay, so that's a 3 right there. All right, now we need to find the gradient of f. So we have to find the gradient of f, and we have to evaluate it at this point, 1, negative 1, 2. So remember that the gradient of a function is a vector that contains the partial derivatives. So the first component is partial with respect to x, then partial with respect to y, and then partial with respect to z. Let's go ahead and get off of this page, and we'll go to the next page. So we have f of x comma y comma z equals xy squared minus 4x squared y plus z squared. So let's find the partial of f with respect to x. Now remember, when we do this, we treat y and z as constants. So this is like a constant multiple of x, which means the derivative with respect to x is just going to be y squared. And then here, this we can rewrite that as minus 4y times x squared. So then the derivative is going to give us minus 4y times 2x. Okay, so minus 4y times 2x is what we have there. So minus, already have a minus, 4y times 2x. And then z is just a constant with respect to x, so z squared is also just a constant, so we just get 0. And then we simplify this to y squared minus 8xy. Now we have the partial of f with respect to y. Let's go ahead and use a new color. The partial of f with respect to y. So here we have x times 2y, and then minus, this is just plain old 4x squared, because now this is the constant factor and this is the variable. And then plus 0, because z squared has nothing to do with x or y, so it just becomes 0 when we differentiate with respect to x or y. So now this simplifies to 2xy minus 4x squared. Okay, and then finally, we have the partial of f with respect to z equals, this is just 0, because there's no z. This is also 0, there's no z. And then plus 2z. So that just becomes 2z. So then overall, we have the gradient of f is y squared minus 8xy, comma 2xy minus 4x squared, comma 2z. Okay, so before we go back to this page, well, let's go ahead and go back to this page real quick. Now we want the gradient of f dotted with our unit vector u. So let's go ahead and clear some room here. All right. So we want our gradient of f dotted with the unit vector u. Gradient of f dotted with the unit vector u. And what we're going to have to do is evaluate the gradient of f at the point 1, negative 1, 2. So before we can do that, we have to evaluate the gradient of f at this point 1, negative 1, 2. So let's go back to this page and do that. So we're going to set aside some space up here. So the gradient of f evaluated at 1, negative 1, 2 is going to be negative 1 quantity squared minus 8 times 1 times negative 1. Okay, and then that's our first component. Then our second component is going to be 2 times 1 times negative 1 minus 4x squared, which is 4 times 1 squared. And then comma, our third component is going to be 2 times 2. Okay, so let's go ahead and simplify all that. Negative 1 squared is 1, and then minus 8 times 1 times negative 1 means plus 8. 1 plus 8 is 9, so we have 9. And then 2 times 1 times negative 1 is negative 2. And then minus 4 times 1 squared gives us negative 2 minus 4, which is negative 6. And then 2 times 2 is just 4. Okay, so here's our gradient vector evaluated at the point 1, negative 1, 2. So let's go ahead and go to page 3 now. So what we need is the gradient of f, specifically evaluated at 1, negative 1, 2, dotted with our unit vector. So that's just going to be 9, negative 6, 4. Oops. Dotted with 6 over 7, 2 over 7, 3 over 7. 6 over 7, 2 over 7, 3 over 7. So let's go ahead and do that. And that's going to give us 9 times 6 over 7 minus 6 times 2 over 7 plus 4 times 3 over 7. So this 9 times 6 is 54. So 54 over 7 minus 12 over 7, and then plus 12 over 7. So these two terms cancel. That's great. And we're just left with 54 over 7. Okay, and that's our final answer. So this has been an example of finding a directional derivative for a given function at a given point in a given direction. And I hope you found this video helpful, and thank you for watching.